Hello dear friends. Today I'll be discussing our another module, that is the module 4. In that I'll be just uploading a small video with respect to refrigeration cycle. So refrigeration, so most of the times we have been through the refrigeration. What is refrigeration? Maintaining the certain temperature for any given condition. Say if it is a hot summer and we expect the temperature of any normal drinking water, say at least about 21 to 22 degrees Celsius. That's the room temperature will be at the home, at least in the morning time it will be 26 to 28. Then as the time goes on, so 10, 11, 12, 1, 2, then the temperature will be the variation. So at that moment we expect at least to have some little amount of cold water. So here the refrigeration process, we are going to study about the refrigeration process, how it is done, and with respect to that we are going to study in detail the different types of refrigeration cycles. In that the first comes the refrigeration cycle. In one word, if you want to define what is the refrigeration, that is, refrigeration is the process of providing and maintaining temperature of the system below that of surrounding atmosphere. Okay. I repeat once again the definition for the refrigeration. If you want to define, the refrigeration is nothing but that is providing and maintaining the temperature of the system below of the surrounding atmosphere. In that the first comes is the refrigeration cycle, that is the Carnot cycle. Here the figure what you are seeing is the Carnot cycle. As we all know, the Carnot cycle is the base for any of the cycle where how the process is done with respect to the cycle. Now here you can see the Carnot cycle. I have just drawn the PV diagram and TS diagram. In this PV diagram you can see the process I have written from 1 to 2, 2 to 3, 3 to 4 and 4 to 1, where it is in the curve process. Yeah, it is in the curve condition where 1 to 2 is nothing but isentropic compression, 2 to 3 isothermal expansion, 3 to 4 is the isentropic again expansion, then 4 to 1 is the isothermal compression. So isentropic is nothing but where neither heat is accepted nor rejected but work is done. Isothermal condition is the one where the temperature is maintained constant. Okay, so here if I go towards the TS diagram, you can see here the TS diagram. In the TS diagram what has happened is, that is 1 to 2, 1 to 2, curve becomes straight, curve becomes straight, curve becomes straight, curve becomes straight. 1 to 2 you have maintained a straight line, that is adiabatic condition, that is isentropic condition what we call. Then 2 to 3 the constant isothermal condition where the temperature is, we are just making it compression. Yes, then later the 3 to 4 and 4 to 1 is maintained. That is, here you can see I have written T1 and a T2. What is that T1 and T2? T2 is the temperature which is maintained at the absorption, that is the heat. Here we are maintaining that temperature at absorption. T1 is the temperature of the atmosphere where the heat is getting rejected. So as per the what it is assumed that in the Carnot cycle that heat absorption and rejection takes place at constant temperature and compression and expansion are isentropic. Okay, constant temperature and the heat rejection takes place at constant temperature, and the compression and expansion are isentropic. Yeah, the compression and expansion are isentropic. So with respect to that, if I want to have a small formula for this one, that is, you can just check here, that is network. How the network is defined here, this is nothing but where it is telling that net amount of heat is equal to net amount of work done. That is the first law of thermodynamics. How much amount of work you do, that much amount of heat is produced, what we call. Now in the network is given by the amount of heat rejected by amount of heat absorbed. Okay, so what is the amount of heat rejected here? In the T1 if you say, you can see here in the isentropic condition here S1 we have written common S1 is equal to S4, S2 is equal to S3. So instead of that we have taken S1, S2. So therefore the amount of heat rejected is given by T1 is S2 minus S1 and T2 is given by S2 minus S1. That's the same has been written here. Then here the nothing but we have just sorry for this one, here T1 minus T2 into S2 minus S1 is been maintained. Then the coefficient of performance is given by heat absorbed by work done. That is nothing but what is the heat absorbed here is here T2 S2 minus S1 divided by work. The net work done is given by T1 minus T2, that is into S2 minus S1. This and this will cancel and remaining is T2 by T1 minus T2. So where we can tell that is where it is we can tell that T2 is lesser than T1. Okay, now if we come to the part of unit of refrigeration, that is unit of refrigeration. Unit of refrigeration is given by ton of refrigeration. Now what is this ton of refrigeration? The ton of refrigeration in simple terms, if I want to define, say take approximately 1000 kg of water. What do you call this? 1 ton of water. To convert 1 ton of water to ice, how much amount of heat I have to extract within 24 hours when the water is at 0 degree Celsius centigrade? Then that is called as ton of refrigeration. Okay, the definition somewhat comes like this. A ton of refrigeration is defined as the quantity of heat required to be removed to produce 1 ton of ice within 24 hours when the initial condition of water is 0 degree centigrade. Okay, then the ton of refrigeration is given by, that is 1000 into 335 approximately, when divided by 24 into 3600, nothing but altogether it comes 3.5 kilojoule per second. Consider the ton of refrigeration in the capacity. Refrigeration capacity is given by 3.5 tons kilojoule per second. Okay, if I consider the ton of refrigeration with respect to that, heat removed from the refrigerator is equal to, that is refrigerating effect, that is therefore heat removed from refrigerator is equal to refrigerating effect, that is nothing but RE kilojoule per kg. So therefore mass flow rate, we call it as mass flow rate is equal to refrigerating capacity divided by refrigerating effect. So refrigerating capacity is how much? 3.5 ton divided by refrigerating effect. With the help of this one I can find mass flow rate. Sorry, it was not clear. Now you can see here the refrigerating capacity is given by, that is 3.5 ton kilojoule per second. Heat removed from the refrigerator is given by refrigerating effect, that is RE kilojoule per kg. The mass flow rate is taken from this one is by refrigerating capacity by refrigerating effect, 3.5 tons by RE. So this is a Carnot cycle. Since as earlier I said, the Carnot cycle is assumed that heat absorption and heat rejection takes place at constant temperature, but this is quite practical if you think it is not so easy. So with this, taking this as a base, so further derivations and the equations has been solved. In my next video I will upload with respect to air refrigeration system working on Bell-Coleman cycle, that is a reverse Breton cycle. Okay, thank you.